So we will go to the next talk. It will be by Dr. Soham Bhattacharya. So Dr. Bhattacharya is now working as a research associate in Daisy, Germany. And in fact, he worked extensively in the SUSY searches using the CMS data. And he will speak on searches for the stops and bottoms. So Soham, please,
hi.
Stage is yours. Please. So there may be some questions in between. I will just look at the chat box. Otherwise, if somebody raises hand, I will. Thank you.
Okay. First of all, thank you for the invitation for the talk. So I'll be giving I'll be trying to give an overview of top and S-bottom quark searches at the LHC. So the plan is to start with a short introduction to supersymmetry and why we should search for the third generation squarks. And I'll talk a bit about the typical models that we search for and the general search strategies that we employ, because we don't have the time to go into the details of all the separate search strategies. And then I'll highlight some of just a few of the top and bottom squark searches from ATLAS and CMS, and also show you the summary results from ATLAS and CMS, which shows all the searches together. Okay, now, so supersymmetry, I still think, is still a promising BSM theory till date, and it holds many different promises. For example, it cancels out the large corrections to the Higgs mass and stabilizes the electroweak scale, like you see here. It can provide a dark matter candidate, at least for the R parity conserving scenarios. It can unify the gauge couplings at the gut scale due to the running of the gauge couplings to use the new particles, as you see here. And it also has the possibility to incorporate gravity. Now, supersymmetry predicts a fermionic superpartner for each standard model boson and the other way around also. However, we don't see any SUSY particle at their standard model counterpart masses. At least we haven't found any at the LHC or even at the LEP. So SUSY must be broken to move the S particles to much higher masses. Now, coming to SUSY at the LHC, in general, most SUSY searches at the LHC are motivated by what we call as naturalness. That is, the corrections to the Higgs mass, which you see here, they are comparable, and their sum is at the electroweak scale, roughly. Which effectively means is that particles that contribute strongly to the Higgs mass correction, they should not be too heavy. Which means that the Higgs which couple directly, they should be of the order of a few hundred GeV. The top and the bottom squarks, which couple via one loop corrections, they can be a few hundred GeV to say a TeV scale, and the gluinos, which enter via two loop corrections, they should be less than a few TeV or so. And the rest of the spectrum is decoupled, that is very, very heavy. And it's this natural SUSY spectrum which brings the masses of some of the SUSY particles within the LHC reach, and that makes it interesting in the LHC scenario. Now, why should we do stop and S-bottom searches? The third generation squark sector serves as a probe to a wide variety of SUSY models. You have R parity conserving ones, violating ones, you have stealth SUSY, you have gauge mediated symmetry breaking models, etc. We know that the tree-level Higgs mass, which you see here, that receives a substantial correction from involving top squark loops, for example. So it's really important to study the top squarks at the LHC to understand the stability of the Higgs mass. And here you see how the Higgs mass varies as a function of the stop mass for different mixing scenarios. So this XT is a parameter which determines the mixing in the stop sector, this mixing between the left and right-handed. And for the maximal mixing scenario, which you see in this upper two curves here, you can get a 125 GeV Higgs, even with a stop mass of say a few hundred GeV, or okay, depending on the amount of mixing it have, it can go up to the TeV scale. Whereas for the no mixing scenario, the stop mass needs to be really, really high to get a 125 GeV Higgs. So in this maximal mixing scenario, you can get this lighter top squarks, and that makes it very important for the LHC scenario. And here I have shown some typical benchmark models that we probe for at the LHC with the pure BINO LSP, then a BINO NLSP, where you have the charge between the Squark and the neutralino. Then you have a Higgsino LSP where you have the degenerate states, and then you have the BINO Higgsino mix where the charge and the chi2, chi3 are degenerate and close in mass to the chi10. Now, how do we really search for at the LHC? Now, a full SUSY model, as you know, has lots of parameters, like order 100 parameters. So that makes it really complicated to search for at a real experiment. So what we do at the LHC is we present a search in what is called as a simplified mass spectrum framework, which is that we consider only those particle masses and parameters that are relevant to the decay chain that we are considering, or the decay spectrum that we are searching for, and set the relevant parameter values like the branching fractions at the chirality lifetime, whatever you want, whatever is relevant to your model, we set those values by hand. And we set the rest of the S particles to heavies. The rest of the S particles, for example, in this benchmark models are set to much higher masses, so they don't interact with these, with our spectrum. And hence we get a decoupled spectrum, and that is what we use to interpret our results at the LHC. Now, for a given SMS mass point, what we do is we calculate the experimental acceptance, which is basically the acceptance time, the efficiency, and we use a standard model prediction, which serves as the null hypothesis, and the observed data to calculate upper limits on the cross-section times branching ratio for a given mass point. Now, you need to do this for each and every mass point, of course. And these interpretations for the simplified mass spectrum models, they can be reinterpreted in terms of realistic model using the HEP data that we provide for the different searches. Now, I've shown here the mass plane of the top squark on the x-axis and the neutralino on lightest neutralino on the y-axis. And you can see that there are several ranges in this mass plane, and several regions in this mass plane, and each of these regions can have different types of decays. So in this high stop mass region, where the stop mass is more than the top mass and the neutralino mass, you can have a stop going to top and neutralino. In this region, you can have a stop going to bottom and a chargino. Then when you go into the more compressed region where the mass gap becomes smaller, you can have the stop decaying to a charm quark and neutralino, or you can have also four body decays where you don't have a lot of mass difference between the stop and the neutralino. And as you see here, each of these different regions with different possible decays, they have very different final state kinematics, and they require dedicated strategies to handle them. Additionally, I have not shown in this page here, you can have R parity violating scenarios where you will not have any neutralinos, for example, in the final state. So all you will have are standard model particles in the final state. So you will have very low missing energy and maybe loss of jets or leptons. So those also require separate strategies to handle. So what are the typical variables that we use, right? I'll be naming some of these variables in my next slides. So I've just given an overview so that you are familiar with the basic concepts at least. So For cases where you have neutralinos in the final state, you can have missing energies or missing transverse hadronic momentum. Then you can also count the number of jets in case your model has lots of jets in the final system. Then you have the effective mass, which is, as the name says, is an effective measure of the mass in the system. Then can have something called S transverse mass, which is a generalization of the usual transverse mass for systems with multiple sources of missing energy. So like transverse mass, this has an upper limit at the parent particle mass. And that can also serve as important variable in decay topologies like this. Now, a general search strategy is the following. We choose your favorite model to search for, whatever it is. We identify the characteristic final states, so the electrons, muons, jets, etc., based on the model. And we first have to select the triggers based on the above. Remember, we can't trigger on everything. If you want to trigger on just a very soft tau or very soft photon, you can't, because the rate will be too high. You need to cleverly figure out what to trigger on and be sensitive to your final state. And the search strategy, as I already alluded to before, that is highly dependent on the model. So for R parity conserving cases where you will have large missing energy due to the neutralino, or in case you can have a gravitino, you can use the missing energy as an important variable, or even as a trigger for that matter. For R parity violating cases, due to low to moderate missing energy, along with lots of jets and leptons, you can use jet number of jets or variables related to jets. For heavy objects in the final state like W or Z or top, depending on how boosted these objects are, you can use special tagging techniques to tag these heavy objects. If you are in the soft region, that is in the compressed region, you have soft objects, then there are dedicated soft object reconstruction and soft object tagging techniques. And then, of course, you have to decide your sensitive variables like the ones I mentioned in the previous slide: HT, transverse mass, MT2, missing energy. You can construct angular variables, etc., based on your model topology. And the latest searches nowadays often use different neural network based techniques. And this is becoming increasingly more and more common at the LHC to use neural net based techniques to improve your search sensitivities. And once you have done this, you select your search region in terms of your sensitive variables, and you select this region such that that maximizes the search sensitivity. Say you maximize S by square root S by square. And once you have identified your search region, you estimate your irreducible background. So what I mean by irreducible is it has those background processes which have a very similar topology to our signal. For example, this topology, TT bar, has a very similar topology to this, for example, as you can clearly see. So typically you estimate these irreducible backgrounds using data control methods or functional fits, etc. And you estimate the systematic uncertainties. You have to evaluate both the theoretical ones and the experimental ones. And once you have your backgrounds and their uncertainties, you compare the background prediction with the observation, and you interpret the results in terms of the SMS model that you are considering. Okay, now that I have given at least a short overview of how we do our searches, I'll move on to a few searches from ATLAS and CMS. This is by no means extensive, but I hope you get a feel for some of the searches from the LHC. I'll not spend much time on this slide because I don't really have the time, but you can find all the ATLAS and CMS SUSY public results from these two links here. Okay, coming to an ATLAS stop search. So this is a search motivated by R parity violating models, where you have the stop decaying to top and a new and chi 10 or a chi 20, and you can the stop can also decay to a chargino NP. And since this is R parity violating, you can see you have only standard model particles in the final state. You can have top, bottom, and S, or you can have a 2B and S in case of the chargino. And several LSP types are considered. And have a Bino LSP, Vino LSP, or Higgsino LSP. And okay, the branching ratios are determined, are set different for each of these cases. And this uses final state using 1 or 2 leptons and a large number of jets. And neural network is used to increase the sensitivity of the regions with at least 1 B-jet, where you will have a very large background from the top pair process. And this here shows the results from this study for the 3 different cases, Bino, Winner, and Higgs cases shown in the 3 different colors. The strongest limits are for the Bino case, which reaches about 1.35 TeV or so in the stop mass. This lower region that is also excluded by the observed limit from the electroweak production. And you can also say the Higgs-Ino and the Wino limits here. This is a CMS stop search, which probes RPV model, which you see here. The stop decays to an chi10 and the top, and the chi10 decays to 3 quarks. And this also has a stealth model where the stop decays to this S tilde, and this S tilde decays to the gravitino and its partner S. And here also you have lots of jets in the final state from these gluons, and you have the tops decaying also, of course. And this search, like the previous one, also uses a neural network. So the output for this is called the SNN, which I have shown here, and it brings in terms of the N jet. So you can see here that the background, which is coming mostly from TT bar, how this is nicely separated from the signal for the RPV, which is shown in red, and for the stealth SUSY model, which is shown in this blue here. And finally, the results are shown here. The left-hand side limit shows the RPV case, and for that the stop mass is excluded up to slightly below 700 GeV. And for the stealth SUSY scenario, you have the stop mass being excluded up to about 900 GeV. So, coming to stop searches with taus, I have shown 2 searches here. The first one is from ATLAS, and in this case, you have the stop decaying to the stop having a 3-body decay where it goes to a bottom quark, a neutrino, and a tau, and the tau decays to a tau and gravitino. So this is a gauge-mediated supersymmetry breaking motivated model with a nearly massless gravitino in the final state, and it searches with 2 hadronically decaying tau. So both the tau are considered to decay hadronically, and the search is optimized to be sensitive to low and to moderate mass gaps between the stop and the tau. So this region, the low to moderate mass gap, that is sensitive to the cases where both the taus decay hadronically, and the search region with 1 hadronic tau, the other tau can decay electronically, that is sensitive to a mass gap, to a comparatively large mass gap between the stop and the tau. So different regions in this mass plane here are sensitive to the different decay modes because of the different kinematics. And so the limits here presented in terms of the stop mass and the tau mass on the y-axis. So the highest stop mass limit reached in the study is about 1.4 TeV or so. We have a CMS search with stops going to taus, in the final state. But here the signal topology is different. This serves as a different, the theory motivation behind this is different, as it targets the high 10 beta and Higgs-like scenarios. And here the stop goes to a tau via a decay to a B and a chargino, and the chargino can decay to a tau, or the chargino can decay to an S neutrino also. And here the binning is done in terms of the MT2. This is the same S transverse mass which I mentioned before, the HT, and the missing energy. And the limits for this study is presented here, and in terms of the stop mass and the lightest neutralino, and the highest limit for the stop mass reached here is about 1.1 TeV. So, and I should mention that this was an Indian effort. Okay, coming to CMS stop search, CMS R parity conserving stop search, which also probes the compressed region. So here you have two different decays. So in large mass gap between the stop and the neutralino, you have the stop decaying to a top and a neutralino. You can also move to the compressed region where you don't really have a lot of phase space to produce the top. So you can have a four body decay like this, where you have a bottom and two other fermions and the neutralino. And this contains the hadronic decay modes of the top only. This search uses a deep neural network based algorithm, which we call a deep AK8. AK8 simply means that the jet radius used to tag these boosted top quarks is 0.8. So this algorithm is used to tag the boosted top quark and the boosted W bosons. And in case the top is very boosted, in case the top is not so boosted, a separate neural network called the deep resolved algorithm is used to tag the resolved top quarks in case the decay products of the top is not confined within a single jet. And to increase the sensitivity for the low mass region, because this low mass region is always a headache to probe. It's really very difficult to probe this low mass gap region. So to increase the sensitivity to this region, an extra ISR jet is required. The results are presented here. On the left-hand side, you see the stop mass limit versus the LSP limit on the y-axis. So this is the first diagram which I'm shown here, and there the stop mass is excluded up to about 1.3 TeV or so. For the compressed region, which corresponds to this diagram, and the limits are shown here. The stop mass is excluded up to 600 GeV, and on the y-axis here shows different delta M or mass gap between the stop and the neutralino, and that's fairly flat here. Coming to a stop search. Before I go on, I should say that I have not shown an ATLAS study here, but ATLAS also has similar studies dedicated to this compressed region, which I'll be showing in my summary results. Coming to the top corridor, so this is the corridor region where the mass gap between the stop and the neutralino is close to the top mass. And this search is carried out in a dilepton final state, and this again uses a deep neural network to separate the standard model top background, because as you see, this will have a huge contribution from the standard model top, and hence it's really difficult to probe this region, and you have to use a neural network to gain the maximum out of your data. So the dilepton transverse momentum, the angle between the leptons, the missing energy, the HT, these serve as the important variables in this network. And here I've shown the 2D limit for the stop mass and the LSP mass, and you can see that the entire region is ruled, the entire region that is considered in this search, that is ruled out by this search. And here I've shown the 1D limit for delta M of 175. So that would be along a line in this diagonal direction. And here also you see for the entire range of stop mass that is considered in this study, this entire range is ruled out. You see the theory here and the observed here. Okay, coming to S-bottom searches. The left-hand side shows a result from ATLAS, which is sensitive to models where the chi10 is Beano-like and the chi20 is a Beano-Higgs-Zeno mixture. So you have the S bottom decay into a chi20 and the chi20 decays to on-shell Higgs and neutralino. And the search variables which are sensitive here are the MT2. And you also have this angular variable called theta min, which is basically the 3D angle of the combinations between either of the two leading taus and either of the two leading B jets. So what this means is, if you look at this plot here, events like Drell-Yan, where the Z, for example, recoils against a B because you have the requirement for a B in this system. For that, the angle between the tau and the jet, in this case the B jet, will be large. So you see the Drell-Yan being populated here. That's not the case for TT bar, which you see populating the lower theta min regions, and the signal becomes, as you see, sensitive here.
So
and the limits
can you wrap it up in 2-3 minutes?
Yes, sure.
Yeah.
So you have the S bottom limit versus the chi20 limit presented here, and the results from this search are shown here versus the result from a previous search, and you can see how this search is complementary to this previous search, which requires at least 3B plus large met, and is able to probe a lower chi20 mass and a lower S bottom mass. You also have a CMS S bottom search where the S bottom decays to a chargino and a top, and the LSP, or the neutralino mass, here is set to 50 GeV, and when you will have off-shell Ws when the chargino mass is below 130 GeV. So when the chargino mass is below 130, because the LSP mass is 50, you will have off-shell Ws. And the search is in 2 jets and at least 2 same sign leptons, and you see the limits shown here, and the strongest limits in terms of the S bottom mass is up to about 900 GeV. Okay, I'm moving on to my summary. So this is the ATLAS S bottom stop and S bottom search summary. So you see there are lots of curves overlaid here. I don't have the time to go into the details, but basically you have dedicated searches for each of these corridor regions, some of which I mentioned in my previous slides. And you have searches in different final stages, 0 lepton, 1 lepton, etc. And all of them combined give you the best possible limits that we have till now. And similarly for the S bottom case also. So the top Squark limits reach up to about 1.2 TeV, and the S bottom limits reach up to about 1.3 TeV. We have similar results from CMS. Here I've shown the stop mass versus neutralino mass plane limits, with the stop going to top and neutralino, but you also have the 1D limits presented here for all the different stop decay channels that are considered, and also S bottom channels. And here also the stop Squark limits reach up to about 1.3, and the bottom Squark limits up to 1.25 TeV, which are quite comparable to what we saw from ATLAS. Okay, that brings me to my summary. As we saw, of the order of TeV scale, top and bottom Squarks are theoretically well motivated, and it is also interesting the LHC scenario to search for this. A variety of top and bottom Squark searches have been carried out at ATLAS and CMS for a whole different slew of models and final states. But unfortunately, there is no SUSY yet. But we are constantly improving our search strategies to probe the uncovered phase spaces, and we have a heavy focus towards machine learning techniques to improve our signal to background sensitivities. And of course, run through is right around the corner, so we expect more exciting results soon. That's all from me.
Thank you, Soham. I see Rohini raising hand. Rohini.
Thanks, Soham, for giving very exhaustive discussion. I had only one question, that in the corridor somewhere, when you look at the B, the 4 fermion, BFF bar, and chi1 naught decays, one can also look for the charm chi1 naught, right? I mean, the loop decays sometimes can compete with the 4 fermion. So have there any analysis of a charm tagging search?
Right. So you have this. You mean stop going to charm Kai10?
Correct. That is the one.
Right,
Okay.
right. So you have these searches here. I did not go into the details of that.
That's okay, but I just wanted to know the status.
Yes. So for this, for delta m less than 80 GeV, the stop mass limit here is about close to 700 or so. Yeah.
So that is being investigated. Okay.
Yes. Yeah.
No, because I was just curious that there are sometimes the 4 fermion mostly works, but there are times and places when the charm Chi1 not actually takes over the 4 fermion decays, and that depends on the various issues such as even the composition of your neutral. So, okay, thanks.
Okay, Satyaki.
Yes. Am I audible?
Yes.
Okay. Yeah. Thanks, Soham, for the nice update. I was wondering if, unless I have missed, is there any recent news from the photon final state as a probe to SUSY? For example, for compressed SUSY, I recall that, for instance, Belanger et al. They talked about quite some years back. They talked about photons being a probe to compress SUSY, and in CMS, I know that there have been efforts. Can you comment on that? If there are recent results from ATLAS or CMS? CMS, I know, but ATLAS.
Not any recent that I know of. Yes.
Okay, because in the list in the slide that you have, I was trying to read through it. Here also, from either from ATLAS or CMS, there is no new results with photons in the final state, right?
Right. Okay. I have not found any from this year at least. Yeah.
Okay, and one other thing, this is maybe technical. So this was your slide 14 or 15, I think, where you talked about AK8 jets and deep networks.
Okay. I think this.
Yes. So CMS is using deep AK8. Is it this one on which you also mentioned that ATLAS has a similar study? Or I'm just curious to know, is this deep AK8 CMS specific, or ATLAS also?
Deep AK8 is CMS specific, as far as I know. Yes. ATLAS uses separate tagging, but I'm not sure about the details of that. But deep AK8 is CMS specific. Sure.
Okay, and okay, yeah, and you have some details of how this type of deep networks are designed, like what goes in deep AK8.
Yes, I mean, yes. The discussion on deep networks would be another talk in of itself, but
yes, of course.
So deep.
Go ahead.
Yeah, so I mean, you of course have lots of sort of variables for your top tagging, for example, and you can have the different jet shape variables on lots of angular variables using the constituents. So all of these are fed into a deep neural network. Yeah.
So we can move on. Actually, it's already 13-14 minutes past the time. So
thanks.
Yeah.
Thank you very much.
So thanks, Soham.